Hi everyone, welcome to section 1.2. We're talking slope. So, first thing we take a look at in terms of slope is a lot of different wording that we see. It can be listed as the change in output over the change in input, delta output, which is the triangle output, over triangle input or delta input, which means the change in output over the change in input. The symbol for the slope is most often used the letter M, and the formula y2 minus y1 over x2 minus x1. Please notice when we have two ordered pairs that we have x1 comma y1 and x2 comma y2. Now you could have called the first ordered pair x2 comma y2, but what you couldn't do is call it x1 comma y2, meaning that the partners have to go together, meaning that if this is an x1, then this is a y1. It'll be more easily identifiable as we do the problems. It'll be better explained. Given the two ordered pairs, we're going to find the slope, also called the rate of the rate of change. We're going to call this first set x1, y1. So I'm going to designate this with the number 1 and designate this with the number 2. On top, from the formula, y2, 199, minus y1, 264, over x2, which is 6, minus x1, which is 1. We end up with negative 0.65 over 5. Now let's talk about units. When taking a look at these units in the description, in New Jersey, the average price in 2020 was $2.64. And in 2020, it was the dollar. In June of 2020, it was $1.99. In January, it was $2.64. I apologize. I should have spoken that a little more clearly. And so what we're noticing here is how much time has passed. So there's 6 months that have passed because it's the first month is represented by the month of January as month 1, and June is represented by month 6. And we notice the pricing was $2.64 and $1.99. Pricing has gone down, so we would expect a negative sign. The negative sign is indicative of something decreasing, which is great. Dollars were used to measure the amounts of $2.64 and $1.99. So therefore, my unit on top better be in terms of dollars, and on the bottom it was in terms of months because my input was months, my output was dollars. So I have this amount, negative 0.65 over 5 months, which works out to be negative 0.13 per month, which means on average we're seeing the gas price decreasing by 13 cents per month. So that's a good thing. I wish it was still going on. Table below shows the distance covered by Daniel during 6 weeks of cardio exercise. So we have 6 weeks, 0, 1, 2, 3, 4, 5, and 6. And we want to figure out the average rate of change covered from week 0 to week 4. So let's take a look at week 0 to week 4. And what we're going to see here. Hey, Josh. Good. Sure. I can. I'm in Jersey. I'm 2.5 hours from you. No, I work. I work during the week. Yeah, I have another job. Yeah. Yeah. I'm sorry. I listen. If I was there, I would gladly come out of my truck and pick it up. It wouldn't be an issue. It's just that. Always, always. Yeah. No, just call up. Just you might want to call up the store if you're not going to make it today, and let them know when you're going to be there, so they don't put the stuff back on the shelves. Yeah. I don't know what to say. I w- right, right, right. I wish I could tell you. I just don't know what to say. Like, you know, I'm not really a mechanic guy. My cars are old, and old cars I could tell you, but I can't tell you anything after like 1985. Um, yeah, I wish I could tell you, Josh. It's not that I live in Jersey, dude. That's why. And I'm two and a half. I'm literally 2.5 hours from you. Not like down the street. Yeah. And it, I'm sorry. I wish I could help you out. I just don't know what to do. If not, just let them know that you'll be there a different day. So they don't put everything away on you. All right, Josh. Thanks. I'm sorry. Sorry, bud. Yeah, when you kick the nuts, they never stop. That's the way life goes. Nothing helps. I'm sorry, Josh. I'm sorry, bud. I'm sorry, bud. I'm sorry. Sounds good, Josh. Hang in there, bud. Bye. So let's take a look here. What is the average from week 0 to week 4? So the total distance traveled here is 14 miles, and the total distance traveled here is 10 miles. So my two ordered pairs are 0, comma 10, and 4, comma 14. So I'm going to do y2, which is 14, minus y1, which is 10, over x2, which is 4, minus x1, which is 0. It's going to be a total of 4 over 4, which is 1. Now I want units on this, so let's take a look here. On the bottom are weeks, so this is going to be in terms of weeks. And on top is going to be the distance in miles. This is going to be miles. So we're going to get 1 mile per week. So on average, we're seeing an increase in cardio of 1 mile per week. The distance covers uh, increases on average by 1 mile per week in the first 4 weeks. What is the average rate of distance for Daniel from weeks 3 to 6? So let's take a look at week 3 to 6. Ordered pairs are 3, comma 16 and 6, comma 13. Notice now that the distance covered is less, so we're going to get 13 minus 16 over 6 minus 3, which in this case gives me a negative 3 over 3, which is negative 1 miles per week. This time the distance covered is going down. Maybe Daniel suffered an injury. The distance covered decreases on average by 1 mile per week from weeks 3 to week 6. So we see a decrease in the amount that's covered. Maybe he got an injury. Maybe he's just tired of working out. Who knows? So that takes a look at our average rate of change. Let's take a look here at the average rate of change. Jose recorded the average daily high temperature in degrees Fahrenheit for his science class during the month of June in Scottsdale, Arizona. The table shows the table below represents the highest temperature on the nth day of June of that year. Show all of your work for each of the following and make sure you use the correct units. So let's take a look here and we'll just select one on average. We'll do letter B. Find the average rate of change between 7 and 11. So we're going to take a look here and 7, comma 107. And here we're going to do 11, comma 114. So 114 minus 107 over 11 minus 7 gives us a total of 7 over 4 which gives us 1.75. Now we need units, of course. So our output is temperature in degrees Celsius, and the number on the bottom is in terms of days. So we're going to say 1.75 degrees Fahrenheit per day. So on average, from June 7th to June 11th, the temperature increased on average by 1.75 degrees Fahrenheit per day. Just looking across here, I see I go from 100 to 103, 103 to 101, 101 to 107. It would be difficult to tell whether or not I have a constant change because my input is not increasing by a steady amount. Here I've increased my input by 1, here I've increased it by 2, here I've increased it by 3. But I could check my slope in two cases. Now in the previous example, I want to show you that, again, my input is changing by 1 each time. 1, 2, 3, 4, 5. So I can see that my increments for my input are increasing by 1. Now my output here increased by 2 and then by 3. That shows that my slope is not going to be the same. So if my input changes by the same amount each time, but my output doesn't, well, then my slope is not remaining constant and I don't have a linear function. If I were to graph that, it would not be a line. It wouldn't just be one continuous line. Here it would be nearly impossible to tell that because my increments are not changing by 1 each time. Let's take a look at our next setup here. 2 to 3, 3 to 4. Look, in each case, we're seeing an increase of just 1. So let's see what happens with our output if our output increases by the same amount each time. So from 1.47 to 1.69, I see an increase of 0.22. From 1.69 to 1.94, the increase is 0.25. I'll know that this is not a linear function. This I can identify because here my inputs are changing just by an increment of 1, as opposed to my input changing by increments other than 1. Because when that's done, I literally need to do the calculations. There isn't any other way to do it. Let's take a look when things are going down over time. After completing a four-year college, Kei Waku has a student loan debt of $32,830. He plans to reduce this debt by at least $2,345 a year. Use this information to complete the table. I'm going to start out with the first part and kind of jump my way down a bit and see how you would do with this. So at year 0, we'd be at $32,830. That's how much money he's going to have in debt. Well, now his debt's not going to go down. It's not going to go up. It's actually going to go down. And the reason why his debt's going to go down is because each year he's going to be paying off some of that debt. And we know that because they've told us that in the problem. It's not intuitive. So in this case, it's going down by $2,345. So after year 1, our debt is only going to be $30,485. I don't need to put units on this because the units are listed above in the description that I'm being told it's in dollars. Let's talk about the input and output variables. So the input variable is the number of years it's going to take him to pay off the loan. Should have said years before, the number of years. So after 1 year, his debt is $30,485. He's paying it off. The output in this case is the amount of dollars. So the number of years you're paying for, you're under control of. Your debt, you're not in control of, or we'd all make our debt 0. Let's talk about the average rate of change. Well, the average rate of change is going to be negative 2,345. I'm going to put that here. I know it asked for it in the previous, but I kind of want to put it here to describe what it means. It's negative $2,345 per each year. So after every year passes, his balance that he owes out is going to decrease by $2,345. That's why it's a negative sign that's placed on that. Let's take a look at linear functions and what they mean. and talk about what makes them linear. As I mentioned before, if the same average rate of change exists for any pair of points, then the function's linear, meaning that if I see that same change all throughout, the slope is constant between any two ordered pairs, then I have a linear function. If it's not, then it's not linear. It should be a regular line that I'm taking a look at, saying it's a straight line. All lines are straight, but that the slope is going to remain constant. And it's difficult to tell on a table if the input is changing. But if the input remains constant, changing by, I shouldn't say remains constant, but changes by a constant amount each time, it's pretty easy for us to tell whether or not it's a linear function, as I showed you above. Let's talk about the behavior of a slope. If a slope is greater than zero, meaning it's a positive slope, then the graph is increasing from left to right. We always read from left to right. And it should make sense to you if it's a positive slope, then we're going to see an increasing function. If the slope is below zero, meaning it's a negative slope, then we're going to see a decreasing function. And if the slope is zero, well, that means nothing's changing. So we're going to see that horizontal line that we talked about. And M is undefined if we have a vertical line. That means the line is straight up and down. We have an undefined slope. In calculations, I'd get a zero in the denominator, which would mean I'd approach infinity, which would mean it's definitely not going to be able to be interpreted. Let's look at criteria for graphing, and that's where we're going to pause off. And let's begin with this. When we get ready to graph, it's very important that we title our graph. And so we want to write what the graph is about. So if somebody looks at our graph, they'll know what it is. For our horizontal graph, we want to label a couple things. We always want to label our axis by putting a unit, by putting a variable there. We want to write down what it represents, and we want to put units down. So if it's time, it's not sufficient to say time, because time could be in hours, minutes, it could be in years, it could be in tens of years. Make sure you use an appropriate scale, and the scale can't change. So if from this line to this line, we're going up by 5, so we call this number 5, we can't go 5, 10, and then suddenly jump to a number like 17. So we'd have to increase by 5s all the way across if we chose the number 5. Of course, we can use a break. So that would mean that if we started out, we said, you know what, my values are increasing each time by 5, but my initial value is 200. Well, then I'd put a break in there. So I'd represent that from there to there, my initial value was 200, meaning that that area was compressed. Some people use double line, some people use a squiggly line. Either one is fine. And then I'm going to go up by 5 each time. That would make this line right here 205, this one 210, this 215. Or I was increasing by 2s. This would be 200, then this would be 202, 204, 206, or any increment you should so choose.